So we're looking at the fifth theorem and the last theorem in module 2. That's maximum power transfer theorem. What are the objectives? Why is that we are learning this particular theorem? Or by learning this, what is that we'll be coming to know? Is to derive the conditions for maximum power transfer to the load in AC and DC circuits. Which are AC circuits? AC circuits are those which involve the inductor and capacitor. Which are DC circuits? DC circuits are those which involve only the resistors. Okay. So under what conditions maximum power would be transferred to the load in such circuits is what we are going to see by deriving the conditions for maximum power transfer. Okay. So this particular theorem tells you under which condition a maximum power would be transferred to the load. What is load? Load is a resistor or the impedance that we connect at the output across which we measure our output. Understand that? So under which conditions we will be able to transfer the maximum power to the load is what we are going to derive in first place. Second is, after finding out the conditions for maximum power transfer, what is the maximum power transfer is also going to be understood here. Okay, first is condition under which the maximum power is transferred, and what is that maximum power being transferred is also something that we're going to learn. Fine with that? Now, there are three cases in this particular theorem. See, first case is you will have AC circuits with impedance ZL. Okay, AC circuits with impedance means load impedance, we should say. So this is just not impedance, but load impedance. Everybody get that point? AC circuits with load impedance. Second case is AC circuits with purely resistive load. There are two types of loads there. The circuit would be same. The circuit would be AC circuits only. But sometimes AC circuit will have an impedance which will have resistor as well as reactance part. Whereas your load could also be purely resistive. Purely resistive means only resistive part, no reactive part. So these are the two cases. And the third case is DC circuit. DC circuit means we'll not be talking about impedance at all. DC circuits means it's only resistive load. But in AC circuits, you can have resistive load as well as load which is an impedance. Okay, so these three cases is what we are going to look at. Case number one, AC circuits with impedance as the load. Case number two, AC circuits with pure resistor as the load. Third one is DC circuits with resistive load. The third one is the easiest because dealing with DC circuits is something very easy compared to the AC circuits. Okay, same applies here also. Now let's see the conditions for maximum power transfer. Conditions for maximum power transfer. So this is a derivation. Derive the conditions for maximum power transfer could be asked. Fine, as a derivation in this particular theorem. See, everybody look at this and you have to see, have we seen this particular type of network anywhere? Anybody would like to answer that? Have you looked at this particular circuit before? Anybody would like to respond to that? No? Where have we seen linear two-terminal network? Linear two-terminal network. Where are the two terminals? See, A, B. What have we done with the terminals? We have connected the load. This is what is the load we are talking about. Okay, so this is linear two-terminal network. Okay, where have we seen this linear two-terminal network? We have seen this linear two-terminal network in Thevenin's theorem and also in Norton's theorem. What does Thevenin tells you? Thevenin tells that any linear two-terminal network can be replaced by a voltage source in series with the resistance or impedance. Voltage source in series with the impedance or the resistance. If it's an AC circuit, you'll have impedance. If it's a DC circuit, you'll have resistance. So any linear circuit by Thevenin's theorem can be written like this: a voltage source in series with the impedance or the resistor. And this is the load that we have connected. Is that okay with you? So maximum power transfer is an extension of Thevenin's theorem, mind you. What is maximum power transfer? Maximum power transfer is just an extension of Thevenin's theorem, where it will be telling us under which conditions we can transfer the maximum power to the load. But understand, Thevenin's is playing a role here. Fine. Where? What is this ZT? ZT is an impedance, right? So if you have to expand this in terms of resistor and the reactance, see, this is how we can do it. ZT is resistive part plus the reactive part. Okay, since it is Thevenin's impedance, we write it as Thevenin's resistance plus J times Thevenin's reactance, because it is Thevenin's impedance. So that is your Thevenin's impedance for you. Okay, now what is that we have connected across AB? We have connected a load ZL. Understand that? So this load ZL can be written as RL plus JXL. If ZT can be written as RT plus JXT, ZL can be written as RL plus JXL. What we have done, we've just expanded the impedances, okay, in terms of the resistance and the reactance. Is that okay with you? ZT and ZL is expressed like this. Fine. Next. Suppose we have to find out the equation for I. What do we do? Where is I flowing? See, I is flowing here. Suppose I want the power. I want power means what? I squared RL or I squared ZL we do, right? Okay. So for that I need I. So how to find out I from this particular circuit? We have to apply KVL. And how does the KVL look like? See here? KVL looks like this. What is it? We have to move along the clockwise direction. When I'm moving like that, you find negative sign, so it's minus Vt. And when we are moving like this, we find Zt. Since I is flowing through that, it's Zti plus Zli equal to 0. So that means the algebraic sum of all these voltages should give you 0, is what KVL is telling us. Okay, so from this, what is our I? I is Vt by Zt plus Zl. Okay, let's express this Zt plus Zl in terms of the resistances and the reactances as we have seen before. Is this much okay with you? So what we have done, we have obtained the equation for I. Where is that I flowing? The I is flowing through the load. Why do we want I flowing through the load? Because I want to see what is the power. Power is I squared R or Vi. Okay. When it is Vi, then also I is needed. When it is R squared I, then also I is needed. So I wanted to see how the I looks like, which is flowing through load. Okay. This I looks like this. Why it looks like this? You apply KVL, obtain the equation for I, which happens to be Vt by Zt plus Zl, and express these impedances in terms of the resistance and the reactance. So it looks like this. Now what we shall do? We shall see here in the denominator, okay, we have real terms as well as imaginary terms. We have RT and RL as real terms, and JXL and J, okay, this is JXT, sorry, this is supposed to be JXT. Understand that this is JXT. Now, RT plus JXT, you have to correct this, okay, RL plus JXL, we have to separate the the real term and the imaginary terms. Let's do that. Okay, so that is not yet done. Okay, but what they're doing is, let's do that in the next place. See that correction is made here. The average power delivered to the load is given by this. This is where I wanted I. The average power delivered to the load is this. If it is I squared R, it is power. If it is half I squared R, it is average power. Understand that. Half of I squared R is the average power. I squared R is the power. So we are looking at the average power delivered to the load. Fine. So we want I here. So let's substitute the I that we have got previously in this particular place. Okay. What is there as I? See here, this is there as I. This is xt. Okay. Just substitute this in place of I. Okay. So let's get that. What is that is there here before substituting I here? So we need magnitude. How to obtain the magnitude of I squared? How to obtain the magnitude of I squared? See here. Let's get I squared plus. Let's get I squared. What is I squared? So you have to just square it. So it's Vt squared divided by this denominator square. Okay, in the denominator, what is being done? What is the difference between this and this? See here, the real terms and the imaginary terms are being separated. The real terms and imaginary terms are being separated. Okay, so it looks like this after that. Fine. Now we have to find out the magnitude. What is magnitude? How does the magnitude looks like from this? You have j term, right? I have to somehow eliminate that j term by taking the magnitude. What is a plus jb? A plus jb is the imaginary number. How to take the magnitude of a plus jb? Magnitude of a plus jb is square root of a square plus b square. So if you want to take magnitude of I squared, what will you do? You will do this. See, it is a square plus b square form. Understand that? See that here? A plus jb, this is a suppose and this is b. A plus jb is there. So a plus jb can be written as what if you take the magnitude? It is, see here, magnitude square. It is this. Understand that since we have brought in the magnitude, soon after, see here it was just I. But what is it here? It's magnitude I. So we have to substitute magnitude I here. Magnitude I squared, it's not I squared magnitude, it's magnitude square. Okay, so this is what it is. So this has to be substituted here. Now suppose this p has to be p max. Now we have got the average power equation. Now for this average power equation to be maximum power, what needs to be done? For this average power to be maximum average power, what needs to be done is the question. For this P to be P max, very important. I have explained to this. I have explained to you about this earlier no, I don't think I have explained this. You just listen to me very carefully. Now, every time we want to obtain the conditions for maximum, it could be maximum power, it could be maximum height, it could be anything. Condition for something which is maximum. What do we do normally? We do differentiation. We do differentiation. What is the meaning of differentiation? Everybody understand this? Everybody understand this? See here, you see this differentiation, right? Del P by del RL. What does that mean? It is partial differentiation of the power with respect to RL. What is this? This is partial differentiation of power with respect to XL. Why partial? Because there are two variables. In this, there are two variables. XL is also a variable, RL is also a variable. Where were XL and RL? XL and RL were in ZL. In ZL, we have resistive part as well as the reactive part. You can go for varying RL, you can go for even varying XL. Understand that? So, there are two ways in which we can see the variation in P. That is, once by varying RL. So when we are varying RL, I'll keep XL constant. And the second case is by varying XL by keeping RL constant. That is why it is called as partial differentiation. Okay, and why this has to be equated to 0 after differentiation? When would this differential be 0? When this P is constant, it would be 0. And when would be the P constant? Listen here. The meaning of meaning of differentiation of P with respect to RL means as you go on varying RL, the P would increase means this would be a positive entity. Everybody understand? This is very important. Differentiation of P with respect to RL means it's variation of P with respect to variation in RL. If this entity is positive, then P is increasing with increasing RL. On the similar grounds, if P is decreasing with increasing RL, then this would be negative. When would this be 0? When this is not varying. Yeah? Anybody? Yeah. When this is constant, this is 0. When when the whole stuff is negative, that means P is decreasing. When this particular differentiation is positive, that means it is P is increasing with increasing RL. When would this be 0? This would be 0 when P is maximum. When would be P maximum? P goes to maximum and it becomes a constant. It would not go beyond that. That is the idea. Whenever any parameter reaches its maximum, it would not go beyond that. That means it will reach the saturation, and when it gets to the saturation level, it's a constant, and the differentiation of constant is 0. That's why we perform the differentiation and then we equate it to 0. This is the condition wherever you go, whenever you try getting the condition for maximum value of something, we do differentiation and equate it to 0. Differentiate with respect to a entity with variation of what the actual parameter is rising or decaying. Understand that? So this is how we can obtain the condition. So this is RP. If you perform this del P by del RL, I have not given all the steps of performing this partial differentiation. I hope you're good enough to understand what is this. Okay. So if you perform this, you will end up getting this equation number 2. That is differentiating P with respect to RL. Differentiating P with respect to RL and equating it to 0 will give you this, and this implies equation number 2. Similarly, performing this differentiating P with respect to XL. Here we differentiate P with respect to RL. Here we are differentiating P with respect to XL and equating it to 0. So if you do this, you'll obtain this equation number 3. You can do that and see. Okay. So once you differentiate it with respect to RL, you will get this particular equation. And again, you differentiate with P with respect to XL and equate it to 0 to get equation number 3. Now, you obtain 3. What is 3 telling you? The load reactance would be equal to the Thevenin's reactance. What is equation number 3 telling you? The load reactance is equal to the Thevenin's reactance. Where is load and where is this? Everybody should remember this. Yeah, there is load here. This is load impedance. This is Thevenin's impedance. This is load impedance. This is Thevenin. What should this load impedance be equal to for maximum power to be transferred is what we are looking at. What should this ZL be equal to for maximum power to be transferred is what we are looking at. Okay, so we have obtained this. In equation number 3, it is telling us that for P to be maximum, when P is maximum by varying XL, we see that the load impedance would be equal to what? The Thevenin's load reactance would be equal to minus Thevenin's reactance. So just if you substitute this particular result in equation number 2, what's happening? This load resistor has to be equal to minus xt is what. So if I substitute this XL as minus xt, what would happen? This would become 0. So you'll be left with square root of RT square. So RL is square root of RT square means RL is RT. Everybody understand that? So equation number 3, if substituted in equation number 2, which says When P is maximum by varying XL, XL has to be equal to minus XT. Okay, so this XL has to be equal to minus XT. That means plus XT minus XT get cancelled. So this becomes 0. You will be left with RL equal to square root of RT square, and that gives you RL equal to RT. This is one condition. What is that? The load resistance should be equal to the Thevenin's resistance is one condition. Fine. Now, equation 3 and 4 are there, right? What is equation 3 and 4 telling you? XL is minus XT and RL is RT. So if you substitute this in load impedance, see what happens? This is the load impedance. ZL is equal to RL plus JXL. So if you substitute RL equal to RT and XL equal to minus XT, it looks like this. Understand that. What is ZT? ZT is RT plus JXT. If ZT is RT plus JXT, what is RT minus JXT? RT minus JXT is complex conjugate of ZT. So we have been obtaining equations now. ZL has to be what? ZL has to be what? ZL has to be complex conjugate of ZT. That means the load impedance has to be complex conjugate of Thevenin's impedance. The load, if you have the load impedance for maximum power transfer, that load impedance has to be equal to the complex conjugate of Thevenin's. What is Thevenin's impedance? Thevenin's impedance is RT plus JXT. But what we have got here, ZL has to be RT minus JXT. What is RT minus JXT? This is complex conjugate of Thevenin's impedance. So this is another condition. This is one condition. This is another condition. Now, suppose the load ZL is purely resistive, we say. Load ZL is purely resistive. That means what? ZL is what? ZL is RL plus JXL. Understand that? ZL is RL plus JXL. In that RL plus JXL, if you say ZL is purely resistive, means this reactive part has to be 0. So when reactive part becomes 0, what would this ZL be? ZL will be RL. I'll just show you that here. You have your ZL here, right? Suppose this ZL is purely resistive, means this has to be 0. This XL has to be 0. So what would your ZL be? Your ZL would be RL. Understand that? That is what is being told here. So substituting this XL equal to 0 into where is 2? 2 is here. So earlier we substitute this XL as minus XT. Now we are taking the condition that what if your load is purely resistive? If your load is purely resistive, this XL is 0. So if this XL is 0, what is this? Square root of RT square plus XT square. What is square root of RT square plus XT square equal to C? What is square root of RT square plus XT square equal to? Here is your ZT. Here is your ZT. What is RT square plus square root of RT square plus XT square equal to? If this is ZT, what is square root of RT square plus ZT square? It would be magnitude of ZT. So that is what is another condition. If XL is 0 into, if XL is 0 into, it would be RT square plus XT square. What is RT square plus XT square? RT square plus XT square is magnitude of ZT. So we have obtained these three conditions. What is that? RL is equal to RT, ZL is equal to ZT conjugate, and RL is equal to ZT magnitude. Understand that? So equation 4, 5 and 6 are the conditions for which the maximum power will be transferred to the load. So these three conditions you need to remember. If it is a DC circuit, the load has to be, the load resistor has to be Thevenin's resistor. If it is AC circuit, the load impedance has to be complex conjugate of Thevenin's impedance. If it is AC circuit and the load is purely resistive, then it should be magnitude of the Thevenin's impedance. Okay, so these are the highlights. AC circuits with impedance ZL as the load. If you connect ZL for maximum power transfer, what should be the case? It should be ZT. What you should connect? Which load you should connect for AC circuit? for maximum power to be transferred, if the load is ZL impedance, then it should be equal to this ZL should be equal to complex conjugate of ZT. First condition. Okay, and though the load is impedance, okay, the power has to be in terms of RL only. Everybody understand this point. The power has to be in terms of RL only. That means the power can never be a complex entity. Understand that? Power can never be a complex entity. Understand that? That is why we consider RL when we are finding out the power or the maximum power. Understand that? So we just consider this. We don't consider the whole impedance. Understand that? Always P max has to be a real entity, not imaginary. That's why we consider only the real part of what? The load. Fine. First. Second, what if the AC circuit is there and load is purely resistive? See, here we connected the impedance. Here we are connecting the resistance. If we connect the resistance, this resistance has to be magnitude of ZT. If we connect the impedance, this impedance has to be complex conjugate of ZT for maximum power transfer. Getting it? That is what is the condition that we obtain. If it is the impedance of AC circuit, this impedance of AC circuit has to be complex conjugate of ZT. If you connect purely resistive load, then this purely resistive load should be magnitude of ZT. And if your circuit is DC circuit, if your circuit is DC circuit, then there will not be question of ZL being connected here because this is DC. The imaginary part will not come. So load resistor has to be the Thevenin's resistor here. The load resistor has to be Thevenin's resistor. Okay, so 3 cases. Let's see the problem. Okay, in all the 3 cases, maximum power is I squared RL only. Okay, see here, in these 2 cases, we are considering the magnitude I, RL, magnitude I because I don't want the J term to be there. So consider the magnitude and consider the real part of load. Same here, consider the magnitude of I, then consider the real part of load. But here we don't say magnitude because this will not be an imaginary entity. I will not be an imaginary entity. So it is I squared RL in terms of DC circuits. Calculate the value of ZL. Calculate the value of ZL for maximum power transfer and also calculate the maximum power. This is how the questions would be. Calculate the value of ZL. See here, you have to calculate the value of ZL for which there will be maximum power transfer. And after you obtain that condition, also find out the maximum power is what they are seeing. So what is this condition? This is case number 1. AC circuit is there. Okay. And we are connecting a load impedance. We're not connecting load resistance, we're connecting load impedance. Okay. So what is the load impedance for the maximum power transfer for this particular AC circuit? So just you have to just separate this load. Okay. And soon after separating, you'll find the 2 open circuit terminals. Okay. Remove ZL. Find the Thevenin's equivalent network across the terminals AB. Okay. After you find the Thevenin's equivalent, connect the ZL, which is equal to the ZT conjugate. Fine. That is what. Then find out power. Okay. Very neatly given all these steps. Let's follow these steps. Remove the impedance ZL. Okay. And mark terminals AB. Here. We have removed the terminals Z. We have to remove this load ZL. Okay. And we have marked the open circuit terminals as AB. So what we have to do across this AB, we need to find out the Thevenin's equivalent network. So this is partially a Thevenin's equivalent theorem. Partially. Okay. So let's find out the Thevenin's equivalent network. How to find out the Thevenin's equivalent network? We have to find out VOC and RT or ZT in this particular case because it's AC circuit. How to find out VOC? Let's find out impedance ZL. To find the Thevenin's impedance ZT, this has to be ZT. Okay, make that correction. So deactivating the independent sources. So we have deactivated short. There were two what voltage sources. We have deactivated that to find out ZT. Okay, so it is 3 minus J4 in parallel with 10 ohms. 3 minus J4 in parallel with 10 ohms. So you will see, you'll get your ZT to be this. This is real part, this is imaginary part. Remember. Okay, now let's find out VOC. Mark VOC. Okay, we have to find VOC. Okay, how to do that is like this. KVL implies what? 3 plus J4I here, 3 minus J4 into I plus 20 plus 10I equal to 0. So I gives you this. I have to find out VOC. I have to mark this particular dotted path. Wherever we find out VOC, the voltage across the open circuit terminals, we mark the dotted path. Okay, we apply KVL along the dotted path. We found out VT. And always remember, the impedance is kept in A plus JB form. Impedance is always kept in A plus JB form, but voltage and current are kept in R theta form, the polar form. Understand this now? So this is the Thevenin's equivalent network. What we need to do, we need to connect back the load. And what should that load impedance be? This load impedance should be complex conjugate of Thevenin's impedance. What is complex conjugate of? See, if ZT is 2.97 minus J 2.16, what is ZT conjugate, ZT star? It is, this minus would become just plus. That is what is written here. See here? ZL is this 2.97 plus J 2.1. If this becomes plus, it becomes conjugate, complex conjugate of this. So you have to find out I. So for that you will apply KVL. You will find out I. Okay. You find out R theta form. If you find out R theta form, this is the magnitude. 1.925 is the magnitude. And when we are finding out the power in the end, we actually go for considering the magnitude of I, mind you. Okay. So this is I. We want magnitude of I. What is magnitude of I squared? This is magnitude. 1.925 is the magnitude. Okay. And what is RL? The load resistance. See here, 2.97. Is that 2.97? Yeah. What would be your Pmax? Pmax would be 11 watts. Everybody understand this point? Okay. So this is how we do this. So what was asked? What is the ZL that needs to be connected for maximum power transfer? The ZL is this. For maximum power transfer, the ZL has to be ZT conjugate, which is this. And after finding out the load for maximum power transfer, what is the maximum power? Is this I squared RL. What is I? Magnitude I, it is this. What is the load? It is this, 11 watts. Similarly, what is the difference between the first problem and the second problem? Calculate the value of RL, they are saying here. And we have connected RL. What was the case here? Calculate the load impedance was the case. Next here. Calculate the load impedance ZL is problem number 1. It's the same circuit we have considered. Same circuit we have considered. You have to find ZL. Okay. So what is that we are doing here in the second problem? RL they have asked. So we have connected RL. It's the same circuit, mind you. Note the load is purely resistive. It's an AC circuit, but the load is purely resistive. If the load is purely resistive, what we need to do? What we need to do? We need to connect what? Load for AC circuit. We have to connect the magnitude of ZT. So if you have to find magnitude of ZT means we need Thevenin's equivalent network here for this. So remove RL. In the previous problem, it was ZL. In this problem, it is RL. Therefore, maximum power transfer would be when RL is magnitude ZT. Okay. Remove impedance. No, it's not remove impedance. It's remove resistance ZL. Okay, all the thing is same. So this is same. We removed RL and we have found out the Thevenin's equivalent network as in the previous case. Understand that? Next, we have to find out RL. What is RL? RL is ZT conjugate. So if you connect this particular RL, no, it's not ZT conjugate, very sorry. It's magnitude of ZT. How to find out magnitude of ZT? It is square root of A square plus B square. See, ZT is here, square root of this square plus this particular square. So you would get this. Understand that? So this is the RL that you need to connect. After connecting this, what is the maximum power? Find out I. Okay, find out magnitude of I. Or magnitude of I is this 1.6377. Okay, substitute that. What is RL? RL is something that we have just found out. Okay, this is how we find out the maximum power. Get that point? So, and in the third problem, what is this? How is this problem different from the first two? So this is DC circuit, not AC circuit. For DC circuit, what load needs to be connected? RL has to be RT. So we have to find out RT, the Thevenin's resistance. So what we need to do? Just remove RL to find out Thevenin's network across AB. Find out VOC by doing this. Very similar problems when it comes to finding out VOC. Okay, so that VOC we have found out to be 80 volts. So we have found out VOC, we have to find out RT. For finding out RT, what you would do? You would open circuit this and you would short circuit this. You open circuit and you have short circuit. See? And one more very important thing, this may help you in internals also. See here, there is a resistor in parallel with the short circuit. There is a resistor in parallel with the short circuit. So what is this particular equivalent is? It's 0. If there is a resistor in parallel with the short circuit, then this 3 ohm resistor is redundant. There is no 3 ohms. So if it, what is 3 parallel short circuit? 3 ohm parallel short circuit, 0. So how does it look like? So this part would be 0. So you'll be left with only 6 ohms. Understand that? So we have found out the Thevenin's network. Connect the load. Okay, load is whatever is Thevenin's resistance is there. The same load is connected. RL has to be the Thevenin's resistance for DC circuit. Find out I. Okay, and find out the maximum power like this. Is that okay with you? Now, just give your attendance if you're not given.